Welcome to our tutorial on Cholesky decomposition, an essential technique in NumPy's linear algebra toolkit. Cholesky decomposition is a specialized matrix factorization method that works specifically with symmetric positive definite matrices. This powerful mathematical tool is widely used in scientific computing, machine learning, and engineering applications where efficient matrix operations are crucial. Cholesky decomposition is a factorization technique that breaks down a symmetric positive definite matrix into the product of a lower triangular matrix and its transpose. The mathematical formula is A equals L times L transpose, where A is our original matrix and L is the lower triangular matrix. This decomposition is unique for each qualifying matrix and provides a computationally efficient way to work with complex matrix operations. For Cholesky decomposition to work, your matrix must meet three critical requirements. First, the matrix must be symmetric, meaning it's equal to its own transpose. Second, it must be positive definite, which means all its eigenvalues are positive. Third, as a consequence of being positive definite, all eigenvalues must be positive numbers. These requirements ensure that the decomposition exists and is numerically stable. NumPy provides a built-in function for Cholesky decomposition called numpy.linalg.cholesky. The syntax is straightforward. L equals np.linalg.cholesky of A, where A is your input matrix and L is the resulting lower triangular matrix. This function returns the lower triangular matrix L such that it equals L times L transpose. Let's look at a practical example. We start by importing NumPy as NP. Then we create a 3x3 symmetric positive definite matrix A with values 4, 12, negative 16 in the first row, 12, 37, negative 43 in the second row, and negative 16, negative 43, 98 in the third row. Next, we perform the Cholesky decomposition by calling np.linalg.cholesky on matrix A, storing the result in variable. The Cholesky decomposition produces a lower triangular matrix L in our example. The result is a 3x3 matrix with values 2, 0, 0 in the first row, 6, 1, 0 in the second row, and negative 8, 5, 3 in the third row. Notice how all values above the main diagonal are 0, which is characteristic of a lower triangular matrix. You can verify the correctness by multiplying L with L transpose to reconstruct the original matrix A. Cholesky decomposition has several important applications in computational mathematics and data science. It's commonly used for solving linear systems efficiently, particularly when dealing with symmetric positive definite coefficient matrices. It's essential in Monte Carlo simulations for generating correlated random variables. Machine learning algorithms use it for optimization problems involving covariance matrices. Additionally, it's crucial in Kalman filtering for signal processing applications, where real-time matrix operations are required. Cholesky decomposition offers several significant advantages over other matrix factorization methods. It's computationally efficient, requiring approximately half the operations compared to LU decomposition. It's memory efficient because you only need to store the lower triangular part of the matrix. The method is numerically stable for well-conditioned matrices, providing reliable results. However, be aware that NumPy will raise a linalg error if you attempt to decompose a matrix that isn't positive definite.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.